So, division. So we want to model 15 divided by 3 equals 5. And let's do it a couple of different ways. So first way I'll do, because this is one of your activities, was the partition model. So when you're writing this down for a test, you should state, this is the model I'm going to use. And then every model basically leads to a question. So can anybody tell me what question the partition model leads me to act out 15 divided by 3? What does the 3 mean in the partition model?
How many groups of 3?
Yeah, not groups of 3, but how many groups? Yeah, so that's the thing. So with the partition model, what this means is we have 3 groups. And the question then is how many are in each group? Question mark is what that's supposed to be there. So to act this one out, we have to make our 3 groups any way you want. Sometimes I like to do that. Sometimes I draw 3 circles. That's not too important as long as you have 3 containers to put stuff in. And then you start depositing the 15 things in there until you can't anymore. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and I don't have any left over. So I can see there's 5 in each group. So that tells me 15 divided by 3 is 5. And if you think story problem, usually when we write down, like people think about what does it mean to divide, they'll say something like, I've got 15 candies, I want to share them with 3 friends. How many does each friend get? That's what this does. So you could say the partition model is about sharing to friends. So each of the 3 friends got 5 candies or apples or whatever we have to share.
What about conceptual model?
So that is a conceptual model. Yeah, so a conceptual model is something that I can physically do. It's based on the concept. The concept of here is breaking things into partitions. So these are my partitions. That gives me 3 rooms to put stuff in. So that is a conceptual model. Okay, so that's one way I could model this. So again, when you do your model, it's a good idea to state which model you're using, and then that model leads to a question. The question should then lead you to draw some kind of picture, act it out somehow to demonstrate what the answer is. Okay. But the model tells us what division means. Division means make some groups and then split up into those groups. All right. There was another model I gave called the groups in model. This is also called, also known as the set model, which I never really liked that name because the partition model is also a set model, but it's just a different kind of set model. So I call it the groups in model. And that's what Ashley was thinking for the 15 divided by 3. How many groups of 3 are in 15? Is the question I want to answer.
Can you just swap?
What's that?
Pretty much just.
It just flips the result, like kind of like multiplication is commutative. It gives us the other version of the multiplication problem. Yeah. Is it 3 groups of 5 or is it 5 groups of 3? Right. So in this one right here, I just have groups of 3, and so I just start putting them together. So typically here, I just write out my 15 things. And then I start collecting groups of 3 of them. And it doesn't have to be in an array, I just chose to do that here. So I get 5 groups of 3. So that 5 is my answer. Now with the other one, I had 3 groups of 5, right? Slightly different orientation, different physical situation. And so another question I might ask on the test is, can you come up with a situation, a story, that ends up being the result of the story of 15 divided by 3? All right, other models. There were 2 other models for division. Does anybody remember either of the other 2? Number line was for addition and subtraction, although you could do this on a number line.
Yeah.
So on a number line, it would be a lot like the groups in model, because I'd be just looking for batches of 3 on the number line.
So you just like do 15 lines and then circle.
Mm-hmm. Yeah, so for a number line, we would draw out the 15. Not a very good number line drawer today. 1, 2, 3, 4, 5. Graph paper helps. And then we start looking for groups of 3. So 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And here I get perfectly back to 0, and then I found 1, 2, 3, 4, 5. So that's just a different version of the groups in, but just on a number line. And that's definitely a cool way to do it. Any other ways we could do this?
Repeated subtraction.
Repeated subtraction would be another way. So we could say division means repeated subtraction. So here we want to subtract 3 repeatedly. So 15 minus 3 is 12. And it's okay, remember, it's okay to stack down, but we don't want to write it out lengthwise. I'm going to go 12 minus 3 is 9. 9 minus, oops, wrong spot. 9 minus 3 is 6. 6 minus 3 is 3. And 3 minus 3 is 0. So I subtract until I can't anymore. And then I found it happens 1, 2, 3, 4, 5 times. All right, there's one more division model.
Missing factor.
Missing factor, nice. So the missing factor model is also what do I multiply by? So we just reconsider the problem as multiplication. So I would write it like this: 15 divided by 3 equals, and then I put a box there. And then if you read it backwards and write it down that way, you get the multiplication. What times 3 equals 15. Now this requires knowing 3's, so you could either go 3 and 3 is 6, and 3 is 9, and 3 is 12, and count that out. But eventually you want to come to the conclusion that 5 has got to be the answer. 5 times 3 is 15. Cool. We talked about 0 in the last class. Since we're on division now, let's go over division with 0 again. There's 3 cases with division of 0. Oops, that's out of order. So I'm going to use a variable, let's call it a, and let's make believe a is not 0. Okay. So for our purposes, it's a counting number. So it could be 1 or 2 or 3 or 4 or so on. So the 3 cases are 0 divided by some number, some number divided by 0, and 0 divided by 0 is the other case there. Which one of these is okay?
First one.
Yeah, the first one's okay. So usually I think about money on that one. I've got no money. I'm going to share with you guys. How much am I going to give each of you? 0. Yeah, there's a totally acceptable answer there. This is definitely 0, no problem. So if I think about money with this one, maybe A is 10. I have $10. I'm going to share it with nobody. How much does each person get? What do you mean? There's no people, right? You can't answer that question. So this is unanswerable. So in math, we say it's undefined. This one is just weird. I have no money. I'm going to share it with no people. How much does each person get? Huh? Right? It's again like weird. But if you look at the missing factor model, this leads to a problem. So with the missing factor model, we would rewrite this as, I'm going to say there's the top 0. I'll draw the bottom 0 in a different color. And then equals a blank box. When I rewrite it, I'm going to get blank box times the red 0 equals the blue 0. So I just do it backwards. So what times 0 equals 0? Anything. Yeah, any whole number works there, which is a problem. There's no unique answer there. Okay. So there might be a test question where I ask you to explain what's wrong with 0 divided by 0, or what's wrong with 7 divided by 0. And then I want you to think about one of the models and just explain what's wrong. Okay, why it can't possibly be. And so here, there's no unique answer. And in arithmetic, there's got to be a unique answer. So we got none. And I went over this in a couple of different ways the other day. I'm going to stop there and not worry about those other ways. But I find to justify any one of these, the missing factor model is like the easiest way to look at it. And talking about money and sharing also helps too in trying to figure it out. Any questions on the 0 stuff? Okay. All right, let's see. What other kinds of questions were on that test? Model-wise test, where did I put it? Right here? Yeah. We got algorithms. Here's an example of a problem we kind of just talked about in class. If I try to do a multiplication, can I do a front-end estimation for the hundreds place versus rounding to the nearest 100? So those are 2 different strategies for estimating it. We'll get 2 different results. I think that's relatively straightforward. Oops, not too far. Let's illustrate subtraction. We've got a couple ways to do that. So what was that problem? It was 7 minus 3. So 7 minus 3 now equals 4. So usually the wording will be something like illustrate and explain why the answer it is, or use a conceptual model to show why the answer is what it is. And it'll always be small numbers. Anytime I throw big numbers at you, I'm wanting algorithms, and I'll state, show me different algorithms. So we want to keep models separate from algorithms, which sometimes can be a problem. So different ways we can model this. The most common way, I think, is takeaway. So starting with 7, take away 3. So we just literally start with 7. And then take 3. And just make a note. That leaves 4. So the takeaway is pretty straightforward. So with the takeaway model, again, we start with 7 and we just get rid of 3 somehow. Cross them out, move them. Comparison's a little bit different. With comparison, we want to know how much bigger is 7 than 3. So here I actually have to draw both sets out. So there's my 7. I try to line it up with my 3, and then I just pair them off. And since they're lined up, I really don't even have to. I can just look and say, well, these guys don't line up, right? So here I can say 4 bigger. So with the comparison model, we end up drawing both of them. Other versions of this are on the number line, or I could say, well, what would I add to 7 to get 3? And so we have a counting back strategy. Would be another way to attack that. All right, let's take a look at multiplication algorithms. And let's suppose we're going to multiply about 276 by 23, for example. So there's lots of different algorithms. Does anybody have one that they like besides the alternative? Oh, that is an awesome one. You want to come up and draw that?
Sure.
Okay. Ashley has a great algorithm that I think we decided it comes from Japan, and it's using intersecting lines to come up with the product. You just make sure you don't push those buttons. It freaks out.
Okay.
And just write with it otherwise. So you can see here, she's got 276 over there, and then here she has her 23. So then you just look at diagonals. And so, let's see, here's the first one, here's the next one, here's the next one, and there's the next one right there. So those give us our place values. So if we look at the intersections here, she's a different color, down here I have 3 things meeting 6 things, so there's 18 in the intersection there. That one can carry up there. Over here I'm going to have, what, this is 7 by 2, so there's 14 there. And over here, what do we have? We have 6 by 2, so that's 12. Oh wait, no, sorry. That's 1, 2, 3 by 7. So there's 21 intersections there. And you can write that in there. 21. There's 12 here plus that 1. So altogether, what are we at there? 34. So we can take that 3 up there. Yep, there is that way. And then over here for intersections, I have 6 there and 14, which is 23. That 2 is going to carry up there. And then I have 4 intersections there, plus the 2 gives me 6. So this tells me the answer has got to be 6,348. Like it? No?
That looks confusing.
Really? You get used to it after you do it a few times. So that's related to another algorithm we do. So let's try it a different way. See you later, Taylor. My favorite one, I think, is the lattice algorithm. So what are my numbers again? I get 276 times 23. So I write my 276 times, and then below that I write the 23. And I use that to make a rectangle. That rectangle is going to have a column for each of the numbers above and a row for each of the numbers on the side. The lattice then comes from me cutting diagonals from the upper right to the lower left. So the Japanese algorithm is just a picture version of this. And you can start anywhere you want. So 6 times 3 is 18. 6 times 2 is 12. 7 times 2 is 14. 7 times 3 is 21. 2 times 2 is 4. And 2 times 3 is 6. So the lower part of each diagonal is for the 1s. The upper part is the 10s. And then we just follow the diagonals to get the answer. So coming down here, I have an 8. 2, 3, 4. 6 and 4 is 10. 11, 12, 13. Carry the 1. So there's my 6,348. I like that one. What do you think, Debbie?
I learned that in 5th grade, and that's
You did?
the only reason. Yeah, that's the only multiplication I use.
That's awesome.
Yeah.
Cool. Congratulations to your teacher for showing that. I think it's wicked cool. It's way more fun than our other one.
I don't even hardly know how to do the other one.
Yeah.
To be honest.
Okay, well, you got to practice it for this.
Yeah.
Yeah. Any other algorithms people thought were interesting or like from the algorithms we went over in my pamphlet? Did anyone try the Russian? Did you look at that one?
Yeah, I don't remember how to do
Yeah,
it.
the Russian's pretty crazy.
Is that really how they do it in Russia?
Oh,
Like in school?
It's taught somewhere, but it's not taught all over the place.
So I was gonna say, I was like, oh,
So let's see, what do we have? 276 times 23. 276 times 23. So what we do is we draw it out sideways like that, and we just draw a line down the middle. And then one number we're going to have to repeatedly cut in half, and the other number we're going to repeatedly double. So then you have to make a choice. Which number do you want to repeatedly cut in half, and which number do you want to double? So somebody pick. What are we going to cut in half? 276 or 23?
276.
276? Okay. So cutting that in half, and I just start writing it underneath. Half of 276. Well, let's see. 2 goes into 2 once. 2 goes into 7, 3 times with 1 left over, and then 16, so it'd be 138. No, wait. Yeah. 138. And then I cut it in half again. Half of 138 is going to be, let's see, half of that would be 6. Half of 18 is 9. 69. Half of 69. Now, 69 is a slight problem. Let's see, 2 goes into 6 3 times, 2 goes into 9, 4 times remainder 1, chuck the remainder. We don't care. 2 goes into 34, 17. 2 goes into 17, 8 times remainder 1, so it's just 8. Ditch the remainder. Half of 8 is 4, half of 4 is 2, half of 2 is 1. Okay. That had a lot of halves. So every time we cut 276 in half, we have to double 23. And we got to keep them lined up. So if I double 23, I get 46. Doubling 46 gives me what? 92. 4, 18, 184. 8. 16, 368. Doubling 8 is 16, carry the 1, 12, 13, carry the 1, 6, 736. 2, 7, 1, 1,472. Hoping we don't make a mistake. 8, 8, 8, 5. All right, did anyone confirm my doubles here?
Okay, you're good.
I'm good, thank you, Ashley. Okay, so the trick now is every time, Oh, there you go. Every time I have an odd number in the half column, I need the corresponding double. So 1 is odd, I need that double. 17 is odd, I need that double. 69 is odd, I need that double. 138, 276, nope. So those are all the doubles I need. So then I add up all of those numbers over there. So 8 and 8 is 16, 17, 18, carry the 1. 9, 10, 16, and 8 is what? 24. Carry the 2. 2, 3, 4, 5, and 5. Uh-oh, something go wrong here?
5 and
Oh, 8. I'm in the wrong column. So 8, 13, carry the 1. 1 and 5 is 6. 6,348, which is the product we got before. And the weird thing is it doesn't matter which one you double and which one you have, as long as in the end you grab any double related to an odd half. It's nuts, but it works. The rationale behind it is cutting things in half isn't that hard, doubling things isn't that hard, and adding is not that hard. So it turns out, like computationally, this is a little easier machine-wise to teach a machine to do than a regular one is. Which is kind of bizarre. All right. We could do a different topic, do Hindu multiplication or expanded multiplication. Anybody have anything they're dying to do?
Quick question.
Yeah.
So you said algorithms for subtraction and multiplication. So on the test, will it have division and addition, or will it just be mixed around?
It's going to be mixed around. Yeah. So you should expect for the test in class, it's going to be, I usually pick 2 different operations for models and 2 different operations for algorithms. So you should be prepared to do any of addition, subtraction, multiplication, or division. All right. What else should we do then? Let's do multiplication. Let's do some subtraction algorithms. All right, is there a particular subtraction algorithm anyone wants to go over? My favorite is equal additions. I love that one.
Could we do the complement?
Yes, that's a cool one. So let's warm up to it. So how about we take 2023 and we'll subtract from that 735. So first, let's just do it with our traditional algorithm, and then we'll try the complement. So we can't subtract here, so we have to borrow. 13 minus 5 is 8. 1 minus 3 we can't do, so we try to borrow there. We can't, so we have to jump way over here and borrow. Make that a 10, borrow, and now we have an 11. So that's going to be another 8. 9 minus 7 is 2. 1 minus nothing is 1. All right, complements. So 2023, 735. So a complement is a number or a set that completes another set to get some finer, some bigger picture. So usually we do the complement out of a place value. So for example, the complement for 735, I would either go out of 1,000 or out of, I guess I'd go out of 1,000 here, because we're in the thousands there. So what would I add to 735 to get 1,000? That's the complement. Well, I would add a 5, right? Once I add that 5, that's going to jump a 1 over to here. So I don't need a 7, I need a 6 there. And with the 7, I'm going to need a 2. So my claim is that if I add 265 to 735, then I'll have 1,000. So once I have the complement, then I add the complement to the number on the top. So 5 and 3 is 8. 6 and 2 is 8. 2 and 0 is 2. 2 and nothing is 2. Now, what did I find the complement out of? What was my goal for the complement? 1,000. So this number should be 1,000 too much. So I take away the 1,000 from it. 1288 should be the answer. That's weird, but it works. Yeah. So the cute thing about the complement for me is when I'm creating it, the first pair of numbers has to add up to a 10. And then the other pair of numbers have to add up to 9 from thereafter, because that 10, it carries over that 1. So I just think, make a 10, then make some 9s. And that's my complement. From there, all I have to do is add. So there's no borrowing involved when I do this. So let's do it again for a different set of numbers. So suppose we had, how about 3, oops, that's my pen. Highlighter. 3,216 minus 1,259. So to make the complement, I generally go one place higher than the place I'm at. So this is 1,000, so I'm going to make the complement out of 10,000. So 9 and 1 would make a 10, and then I have to make 9s. So 5 and 4 make a 9, 2 and 7 make a 9, 1 and 8 would make a 9. So 8,741 is the complement, or 1,259 out of 10,000. So then we add the top two numbers. So 1 and 6 is 7, 4 and 1 is 5, 7 and 2 is 9, 8 and 3 is what, 11? But how much over am I here? 10,000, so we just get rid of the 10,000, and so this has to be the answer, 1,957. So that's the complement method. Compare that to, say, equal additions. $3,216 on spot minus 1,259. With the equal addition methods, I just add 10s top and bottom. So 6 minus 9 I can't do, so I add 10 by making that a 16. Down below, I add 10 by making the 50 a 60. 16 take away 9 gives me, what, 7? I can't do 1 minus 6, so I put a 1 there. Increasing over here, I make that 2 a 3. So I always jump to the next column to increase. Now, just to note here, that 1 is really a 10 in the tens column. 10 tens is really 100, right? So that's why that works there. 11 take away 6 is 5. Can't do 2 minus 3, so I make that a 12 and that a 2. 12 minus 3 is 9. 3 minus 2 is 1. So the answer is 1957. So you got to look through the algorithms in the book, look through the algorithms we did in class. There's a couple of algorithms I didn't cover on that worksheet I gave you. You got to find 2 algorithms besides the standard one that you feel comfortable doing. Okay. Any 2 you want. I don't care what they are.
So this is 3 here, just 2. Or 2 and the normal?
You could do the normal one, yeah. So I'll do something like say, show me 3 different ways to subtract 1,259 from 3,216. And you can do any 3 ways you want. My recommendation is one of those be your standard algorithm. Yeah. Okay. Anything else you guys want to do? So either I can make up stuff to do, or you guys can go home early and catch up on homework or whatever else you need to do.